I would like to mention a few things about chemistry. Regardless of what we do, we still reach the element, and reaching the element is the prerogative of chemists. And here, perhaps, is the start of the most interesting process, because chemistry is the science of the atom. We spent a lot of time racking our brains about how to obtain a superheavy nucleus. When we obtained a superheavy nucleus, we also obtained a superheavy atom, which can be studied more subtly, more intelligently, and more elegantly by chemistry than we do in nuclear physics. Here is the periodic table containing all obtained elements, which filled up to the so-called seventh period. And now the question is how they fit into this table. But here I would like to point out that, when keeping in mind the fact that quantum electrodynamics is an exact science, today all elements in the periodic table can be calculated. By the way, Dirac and Fock executed these calculations long ago. Vladimir Alexandrovich Fock even wrote an analytical formula with which he could calculate all the properties of all elements for any atomic number, including all periodicities: the boiling point, melting point, and so forth. This calculation was made, and it is shown here, what the periodic system of Mendeleev would look like if we continue to calculate according to the Dirac-Fock formula. It is shown here. There will be lanthanides, known actinides, then another row will appear, and then another. In general, they calculated up to 172 elements before collapse occurs. This is due to the decay of the vacuum that I have spoken about. But they calculated it in a non-relativistic approximation. This is probably not correct, because when we arrive at a heavy nucleus, for example at element 112, its energy, E sub kx, will be 240 keV, while the resting state energy of an electron is 511 keV. The energy of an electron in the k orbit already becomes comparable to the rest mass. According to Einstein, the mass will change, and there will be a so-called relativistic increase in mass. This relativistic increase in mass must be taken into account in the calculations by Dirac and Fock. But it is not very easy to do so. And this is one of the serious problems of chemistry. We will talk about this problem in depth, because this relativistic increase in mass should manifest very strongly when it comes to superheavy elements. How strongly? For example, if we take the wave function of the last electron in the electron shell and draw this radius of the wave function, then in the non-relativistic approximation, it will grow as Z1/3. But in the relativistic approximation, the nucleus begins to shrink, and the radius begins to decrease. If we move forward until the moment of collapse, then at this moment the electron density would be 10 times higher. And this relativistic effect changes the structure and changes the quantum numbers of all electrons in the orbit. That is, of all electrons, including the last electron, which is responsible for chemical properties. We were already aware of this relativistic effect. We know that there are two groups of metals in the periodic table. One group of light metals, aluminium, copper, fluorite, and iron, which oxidize well. And then there are heavy metals, lead, bismuth, gold, and mercury, which do not oxidize well, but they react well with each other. This is a consequence of the relativistic effect. That is to say, gold is gold because of the relativistic effect. Mercury is liquid at room temperature because there is a relativistic effect. But so far, it is only gold and mercury. If we move even further, gold is located somewhere here. and this effect grows like z squared. And then there may already be quite serious changes in the chemical properties of elements in this region. How big the change will be is a good question. There were articles that showed that the changes will be so great that maybe these heavy atoms will begin to move from their position. That is, the law of periodicity will be violated. And as a result, it is possible that, for example, elements 112, 113, and 114 will not correspond to their light homologues, as it follows from the law of periodicity of Dmitry Ivanovich Mendeleev and the calculations that are made in the non-relativistic approximation. The periodicity table ends with these elements, and they become more and more inert, and they seem to have shifted towards the noble gases, towards element 118. This signals the sudden end to this periodicity.